Thanks a lot to the organizers for having me here. It's a huge pleasure to be physically at the conference, and I'm enjoying the conference so far. So I'm going to talk about a joint work with Jingyin Huang, in which we study right-angle Artin groups from the point of view of measured group theory. So I think these are an interesting class of groups to study from this point of view, first of all because of their basic definition, and they've actually been studied a lot from the point of view of geometric group theory because they have nice actions on cat-zero cube complexes, but not so much, to my knowledge, from the point of view of measured group theory. And somehow the point of my talk is going to be to try to convince you that they are interesting to study because they display a very subtle mixture of rigidity phenomena and flexibility phenomena. And somehow one wants to understand the subtle line between rigidity and flexibility in this setting. So let me start by recalling the definition. So we're given a finite simple graph gamma. So by simple, I mean that you have no loop edge. So you cannot have a vertex with a loop attached, and no multiple edges between vertices. So two vertices are joined by at most one edge. You cannot see this. And then the right angle Artin group associated to the graph gamma, and I abbreviate this as RAG in the sequel, is the group defined by the following very simple presentation. So you have one generator per vertex of the graph. And then the only relations is that you say that two adjacent generators commute. Right? So whenever you have an edge between two vertices, you declare that the corresponding generators commute. Right? So for example, I don't know, if the graph is a complete graph, then all generators pairwise commute, and you get a free abelian group. And at the other extreme, if the graph is totally disconnected, then no generator commutes, and what you get is a free group. And it's often said somehow that RAGs kind of interpolate between free groups and free abelian groups, but they actually form a very vast and rich class of groups, and some of them are actually quite mysterious. For example, the RAG associated to this graph is often an interesting object of study. Or maybe let me mention one striking result about this RAG that was proved by Jingyin Huang. So he proved that the RAG associated to this graph is super rigid for quasi-isometry, meaning that whenever you have a finitely generated group which is quasi-isometric to G gamma, then it's actually commensurable to the group. And somehow this result, so he didn't prove this just for the pentagon RAG, it's for infinitely many of them, but this is one example. And somehow this result was a motivation for trying to understand whether similar phenomena could happen from the point of view of measure equivalence instead of quasi-isometry. Okay, so let me maybe recall a few definitions. So recall that two actions of countable groups on standard probability spaces are said to be orbit equivalent if, well, basically they have the same orbit structure, which means that you can find a measure space isomorphism between x and y, which sends g orbits to h orbits, such that for almost every x in x, if you look at the g orbit of x and look at take its image by f, then you're going to get the H orbit of f of x. And there is a weaker notion, which is that of stable orbit equivalent, where you require that the orbits are not the same on the whole space, but only after restricting possibly to a positive measure subspace. So if you can find a subspace x1 in x and y1 in y of positive measure, not necessarily the same measure, and a measure scaling isomorphism from x1 to y1, which sends orbit to orbit in the sense that if you take almost every point in x1, you look at its g orbit, you take the intersection with x1, and look at the g image, then this is going to be the intersection of the h orbit of g of x with y. Right, so the orbits only coincide after you restrict to these positive measure subspaces. And the following is characterization of measure equivalence in the sense that was defined by Romain in his lectures. So two countable groups are measure equivalent if they admit free probability measure preserving actions on standard probability spaces which are stably orbit equivalent. So this characterization was essentially proved by Cirm with an additional argument by Damien Gaboriau for the freeness of the action. Okay, and so the question we ask is whether it could be possible to prove rigidity results for right-angled Artin groups from the point of view of measure equivalence, or maybe get a measure equivalence classification result within the class of right-angled Artin groups. Okay, so let me already break the suspense and tell you that the answer to the first question is no. No rag can ever be super rigid for measure equivalence. And I'm actually going to explain you two ways of building groups that are measure equivalent to a given right-angled Artin group, but not commensurable to it. So the first construction essentially boils down to the celebrated theorem of Austin and Weiss, saying that any two free ergodic probability measure preserving actions of countably infinite amenable groups are orbit equivalent to one another. So you see that this already says that those basic right-angled Artin groups are far from being super rigid from the point of view of measure equivalence, because they are measure equivalent to any amenable group. But in fact, I claim that this failure of rigidity on the most basic example is a source of failure of rigidity for all right-angled Artin groups. And this is maybe better phrased in the larger context of graph products. So let me give the definition of a graph product, which kind of generalizes the definition of a right-angled Artin group. So again, you have a finite simple graph gamma Yes. Do you have a question?
Definition of a measure scaling isomorphism.
Oh, so it's just, well, so it means that you have a measure isomorphism after you rescale the measure of x1, for example, so that it's equal to the measure of y1. Yes. Well, no, it's more than a non-singular. It's more than that. It's really like so you have a measure on x1, you rescale it so that it's equal to the measure on y1, and then you really have a measure space isomorphism, sending the measure of x1 after rescaling to the measure on y1.
Rescale them to the
probability measure, for example, yes. Right. Okay. Okay, so I'm given still a finite simple graph, and now attached to every vertex of the graph is a certain vertex group, GV. Then the graph product of the groups GV over the defining graph gamma is going to be the group that basically is generated by the vertex groups, and where the only additional relations that you add is that whenever two vertex groups are joined by an edge, then you declare that they commute. Right? So in other words, you start from the free product of all vertex group GV, and then you declare that G and H commute whenever G belongs to GV and H belongs to GW, and there is an edge between V and W. Right, so for example, RAGs are exactly graph products where all the vertex groups are isomorphic to Z. And now, so our first observation is that basically orbit equivalence passes to graph products. So this is something we prove by adapting an argument of Damien Gaboriau, who proved it in the case of free products, but it actually extends to graph products. So basically, you have your defining graph gamma, and you have two collections of countable vertex groups. And what happens is that if they are pairwise orbit equivalent, then their graph products are going to be orbit equivalent. So if you assume that for every vertex of the graph, GV and HV have orbit equivalent free probability measure preserving actions on standard probability spaces, then so do their graph products. We call this G and H. And in particular, the associated graph products are measure equivalent. So in particular, if you combine this with AustinVices theorem, it tells you that if you start with any right-angle Artin groups, then you can always change the Z vertex group here to any amenable group, and you're going to get something which is measure equivalent, but not commensurable to this one. And in particular, if you even choose the vertex group to be just free abelian, well, what you get is again a right-angle Artin group, right? Because I could also have written it as the right-angle Artin group defined by this graph. And so this is saying that even within the class of rags, you don't have rigidity at all. Any single rag is measure equivalent to infinitely many other rags that are not commensurable with it. Okay, I can actually give you a quick proof of this proposition, because it's actually a nice argument. So maybe I can argue one vertex at a time. So let's assume that the two graph products only differ at one vertex. So there exists V such that GV is orbit equivalent but not isomorphic to HV, but maybe for every other vertex they are isomorphic. And I want to build orbit equivalent actions of G on H.
Another question, are two rags commensurable only if they have the same graph?
No. No, in general not. You can have, there are constructions of, you can have one rag being finite index in the other. So it's true that two rags are isomorphic if and only if they have the same defining graph. But it's possible to build two rags, one of which is finite index in the other. I mean, for example, three groups are all commensurable to one another, but they have different defining graphs. But the thing is here, as you as you replace this vertex by Zn with n going to infinity, you're going to change the maximal rank of a free abelian subgroup in the rag, and in this way you build an infinite family of rags which are pairwise non-commensurable. Okay, so I'm going to start with my favorite action of G on a standard probability space Z. Take, for example, the Bernoulli action. And so I'm not going to build an H action which is orbit equivalent to this one, but I'm first going to slightly modify the action before doing it. And for this, I'm also going to give myself two orbit equivalent actions of GV and HV on a certain space Y, which exists by my assumption on the vertex groups. And now, let me write it here. I'm going to consider the following new action of G on the product Z cross YV. So what is this action? Well, the G action on Z is exactly the one I started with. And what is the G action on YV? Well, the thing is, whenever you have a graph product, there is always a retraction from G to any of the vertex groups, which is defined by, you simply take the identity on GV, and you send any other factor to the identity, and this defines you such a homomorphism. And then G is going to act on YV via this retraction. Right, another way of saying is that here I consider the projection math to YV, then the diagram here is equivariant. Okay, and now my goal is to build an H action on X, which is orbit equivalent to the G action. So notice that because each hw with w different from v is isomorphic to hw, I already have actions of the hw's on x, which come from the g action. And really, I only need to tell you how hv is going to act on x. So we're going to define the action of hv on x in the following way, using the projection. So what do I need to do? So here is my space x. I pick a point in x, and I pick an element in hv. I need to tell you where h is going to send x. Well, the thing you do is you use the projection to yv. So you have a projection here, and there h is acting. So h sends this point to another one. But now, because I have orbit equivalent actions of hv and gv, which are free, there is a unique element of gv, which is doing the same thing on yv. And this element acts on x, and this is how I'm going to define the h image of x. By looking at the projection and looking at the element of gv acting at in the same way in the projection and using that element in x. And if you do this, well, so I claim that this indeed defines an h action, an action of hv. And the claim is that if v and w are joined by an edge, then the action of hv on x and of hw on x that we've just defined commute. Which is actually not difficult to check. It's just coming from the fact that the action of hw here is trivial. Which means that if you take h prime in hw, so it's moving the point x here, but it's the same projection. So it means that to define h of this point, you're actually using the element g, and then the diagram closes up. So these actions commute, and therefore it extends to an h action, which by construction is orbit equivalent to the g action. And it's also not very hard to check that it's free using the graph product structure. If you had an element of h fixing a point, then you would have an element of g having the same normal form in the graph structure and fixing a point, and therefore h has to be the identity. Okay, so this gives you a first way of building many groups that are measure equivalent, but not commensurable to a given rag. So we have a second construction of such groups, which is of very different flavor, much more geometric. And so I told you in the beginning that rags have been studied a lot by geometric group theorists because they have actions on cat-zero cube complexes. So here is actually the construction. So if you have a defining graph gamma, you can construct the so-called Salvelli complex of G gamma, defined in the following way. So you start with a vertex then you're going to add a loop per vertex of the graph, per standard generator. So you have as many loops here as vertices in the graph. And then to encode the relations, whenever you have two adjacent vertices, so the two elements should commute, and therefore you're going to glue a torus here. So that in the universal cover, you're going to get something whose fundamental, so that this will have the right fundamental group, the right angle Artin group. So more generally, whenever you see a k clique in the graph, you glue a k torus here. So glue the k torus per k clique in gamma. So you get a complex whose fundamental group is the rag you started with. And it turns out that its universal cover has the structure of locally finite ket0 cube complex. So it's some form of negatively curved space. And the thing is, because this complex is locally finite, its automorphism group is a locally compact second contable group. And our second observation is that whenever G gamma is non-abelian, the automorphism group of the universal cover of the Salvetti complex will always contain an infinitely generated lattice, which is therefore non-uniform since it's infinitely generated. And therefore, such a group being a lattice in the same locally compact second contable group as G gamma will be measure equivalent to G gamma, but of course not commensurable because one is finitely generated and the other is infinitely generated. We actually don't know whether you can build finitely generated examples of such, and we actually suspect that, that you cannot. So I'm not going to prove it, but maybe I can tell you what's the idea just in a few words. So first, it's a well-known fact that there exists such infinitely generated non-uniform lattices in the automorphism group of a tree. So I guess here I should quote work of Bass and Lubotsky, and probably also the seminal ideas of Jean-Pierre Serre. And simply the rough idea is that whenever G gamma is non-abelian, so you have two generators that do not commute, and these yield a tree in the universal cover of the Salvetti complex. And somehow the task is just to extend a lattice acting on a tree to a lattice acting on the whole Salvetti complex. Right, so you start with your rag, which is not non-abelian, maybe this one. You can find two generators that do not commute, and therefore actually generate a free subgroup of the rag. And as before, you have a retraction from the whole rag to this free subgroup generated by V and W. And the thing is, so between the Salvetti complex and its universal cover, you have an intermediate cover, which is the cover corresponding to the kernel of H, where basically what you've done is you've just developed the tree corresponding to this free subgroup, and then at each vertex you still have the other loops attached. And maybe some are glued by tori, and maybe you have annuli here also. But basically, so the idea is that you start with a lattice in the automorphism group of a tree, extend the action to X, and then take the set of all pre-images of coming from the action on X, and this is going to give you a lattice in the automorphism group of the universal cover of the Salvetti. Okay, so this is basically the construction. Okay, so I hope that at this point I've convinced you that rags are far from being rigid from the point of view of measure equivalence. Well, I think what we do still raises some interesting questions. For example, we do not know whether there could be super rigid for integrable measure equivalence, right? Because you see that the first construction involved replacing Z by another amenable group, but Z is distinguishable from other amenable groups by integrable measure equivalence. And here we actually don't know whether we can build finitely generated examples by this construction. So the
Finitely generated example, do you mean finitely generated nonuniform lattice or from finitely generated lattice that we know from each other to...
Okay, that's a good point. So I guess I have in mind finitely generated non-uniform lattice, but somehow, essentially, the quasi-isometric superrigidity statement is going to tell you that the uniform lattices are commensurable with the rag. If you have a uniform lattice, it's quasi-isometric to the rag. So, I mean, again, it depends on what conditions you are willing to impose on the right-angle Artin group, but for the generic ones, somehow they are quasi-isometric, super-rigid. Okay, so what we do goes in a slightly different direction. And we do prove rigidity classification result, but by restricting to a further subcollection of the right-angle Artin groups. So our main theorem is the following. So you take two right-angle Artin groups, and then the crucial assumption is that we're going to impose some algebraic rigidity by imposing that they both have a finite outer automorphism group. And then the two rags are measure equivalent if and only if they are actually isomorphic. So here it's really isomorphic in view of the question I had. If you have two rags with finite outer automorphism groups that are commensurable, they're actually isomorphic. So you see, so this assumption is really crucial and quite sharp, as in the case of the pentagon, it's true that the pentagon rag has finite outer automorphism group. But if I blow up a Z squared here, I'm creating an infinite order automorphism, which is just a transvection sending one of the generators A of this Z squared to AB. So it's really important to assume that both regs have finite outer automorphism groups in this statement. And okay, so let me make a few extra remarks on this statement. The first thing I want to say is that the exact same classification holds for quasi-isometry. And this is a result that was proved in some cases by Besvina, Kleiner, and Sergeyev. And in full generality, the same statement where ME here is replaced by quasi-isometric was proved by Jingyin Huang. The second remark I want to make is that this condition of having a finite outer automorphism group is actually somehow generic. If you take a graph at random, and well, you have to say what it means, but generically you expect that the reg will have a finite outer automorphism group. And not only it's something which is generic, but it's also something that you can actually easily check from the defining graph. Since Lorentz and Servatius proved that the outer automorphism group of a rag is generated by 4 types of automorphisms. So first of all, whenever you have a graph isomorphism, graph automorphism of gamma, well, it induces an isomorphism. Okay, it induces an isomorphism of the rag. And also you have inversion, sending one of the generators to its inverse. So those form a finite subgroup in the automorphism group of the rag. And then you have 2 extra classes. So you have transvections, which consists basically of taking one of the generators and multiplying it on the right by another generator, except that you cannot always do this. This doesn't always define an automorphism. It only defines an automorphism when everything that commutes with V also commutes with W, which is something you can read on the graph. It means that every vertex at distance 1 from V should be equal to W or at distance 1 from W. So which is quickly written by saying that the link of V is contained in the star of W. This is exactly the condition I just said already. So you see, for example, in a pentagon, you never have such a configuration. So those transvections do not appear. And there is one last kind of automorphism, which is partial conjugation of a connected component of the complement of the star of vertex by V whenever you have a vertex whose star, so the ball of radius 1 around the vertex, disconnects the graph, which is also not the case here. So you can easily check in practice whether your rag has finite out or not. Okay, maybe there is a last remark that I can make orally, because so I haven't talked about operator algebras that appear in the title of the conference. So in fact, because rags are cubical, here you can replace having orbit equivalent actions by having W star equivalent actions or stable W star equivalent actions. And you will get the same state. Okay, so let me briefly tell you about the ideas that enter the proof of our theorem. So the first thing we use is something that kind of plays the role of the same role as the curve graph in the theory of mapping class groups. It's the extension graph of gamma, which is a graph defined in the following way. So you have one vertex per cyclic subgroup generated by a standard generator, and more generally, one vertex per conjugate of those subgroups. And then you draw an edge between them if the corresponding subgroup commute. Okay, you see in particular that by definition of the group, the graph gamma embeds in the extension graph, but I actually have much more in the extension graph because I have all the conjugates of the standard cyclic subgroups. And actually, G gamma acts on the extension graph where the action is induced by the conjugation action. Okay, and maybe I can write here the important theorem of Jingyin that we are using, which is that if two rags have finite out, and if they have the same extension graph, if there is a graph isomorphism between their extension graphs, then the rags are actually isomorphic. And what we really do is, out of a stable orbit equivalence between actions of G1 and G2, we build an isomorphism between their extension graphs. Okay, and now to build this isomorphism between the extension graphs of the rags, the key lemma is the following. And for today, let me just state it under the additional assumption that the graph gamma is triangle free and square free. Otherwise, the statement is a bit more involved, but it will already give you the spirit. Okay, so you take a subgroup of the rag. Now I'm claiming that the following two statements are equivalent. The first is that H is the centralizer of a subgroup which is a conjugate of a standard cyclic subgroup. In other words, H is a point stabilizer for this action. And the second is a purely algebraic characterization of those. So let's see, what does this look like? So you have a vertex, you have its link, and as I'm assuming that the link is triangle free and square free, really here you have no additional edges between the vertices. So this subgroup is really Z cross a free group. And I'm basically saying that having a subgroup which is of the form Z cross a free group is enough to know that it has to be a point stabilizer in this graph. So this is equivalent to saying that H is non-amenable, and it normalizes an infinite amenable subgroup of G gamma. And maybe I should add that H is maximal with respect to those properties to be sure that I get the full centralizer, not just a subgroup of the centralizer. Okay, so this gives a purely algebraic characterizations of point stabilizers for this action. And actually what we do is that we also have a version of this lemma for sub-equivalence relation. Which means that, so in the setting of the theorem that unfortunately I erased, so if you have, say, an orbit equivalence between two actions of two rags, well, you can look at the sub-equivalence relation, which corresponds to only restricting to the action to a point stabilizer of this graph. So you have a sub-equivalence relation. And we actually have some purely groupoid theoretic characterizations of this sub-equivalence relation, which enables us to say that it's also going to be a point stabilizer for the action of the other rag. And in this way, we build the map from the extension graph of gamma 1 to the extension graph of gamma 2. And then we conclude using Jingyin's theorem. Okay, so I'm already out of time, so I'm not going to give you the proof of the lemma. But maybe let me just say in a word that, so in the proof of this lemma, we're really using the negative curvature coming from the action on a cat0 cube complex. So typically, we are using this infinite amenable normalized subgroup to get an A-invariant probability measure on some compactification, the Roller compactification of the cube complex. And then one needs to analyze this probability measure to show that essentially, well, either it lives in a product region which corresponds to a line times 3 that corresponds to one of those things, or it has to be supported on exactly 2 points, but then this is going to be H-invariant, and because the action on the boundary is amenable, it's going to contradict the non-amenability of H. So the proof is really via an analysis of probability measures on the boundary of the compactification of the negatively curved space on which the group is acting. Thank you.
Okay, thank you. Yes.
Yes. So when you spoke very quickly about Wstar, so you said you can recognize NE by stating Wstar. Can you
Yes. So the question is about my comment that why can you replace orbit equivalence or stable orbit equivalence in the main theorem by Wstar equivalence or stable Wstar equivalence, meaning that the von Neumann algebras defined by the actions are isomorphic. And so, right, so this follows from something which is independent on our work, which is that if you have a group which is acting properly, non-elementarily in a cat0 cube complex, then it will be what you call theorigid. One way of saying it is that it's both properly proximal and weakly amenable. I don't know if it also maybe follows from work of Horbez and Weiss in different ways, but so it's a general independent statement about group actions acting on cubical spaces.
Okay, other questions online? Okay, so let's thank the speaker again.